Let's start. So I guess let's start with just a survey. Who has read the spec? I know Daria did. Like maybe you can raise a hand or something.
Quick read.
Okay. Who thinks they understood the spec? All right, less hands. And how many people had a chance to actually read the pull request? Okay. That's not zero, which is already good. Let me share the screen and I will try to walk you through how I understand it. What is the kind of the idea, the implementation, and then how we actually get there. I think I can open diagram. There should be a link somewhere here. So the idea is in the previous consensus is to basically take the history of the blockchain, write it somehow to disk, and then audit the disk somehow such that we can prove that users, farmers store the data, and then they will be participating in consensus. So just like in version 1, we have this concept of verifiable sector construction. So there is some kind of mechanism that for your identity of the plot, you can select pieces for a particular sector by some algorithm, and then you get those pieces. In this case, we have 4 of them, different color. I hope it is readable for you. So every piece contains a record, which is these 2 chunks. Our records are sliced into chunks. And then there's also commitment, which is basically all of those chunks committed to using KZG. We create a polynomial, then commit to it. And then we have a witness, which is the proof that this commitment is part of the segment commitment in the global history of the blockchain. So these are basically our pieces. We have 4 of them. And we pretend that every piece has just 2 chunks in the record and not more of that. And then we do some transformations towards the bottom. We basically have a sector. This sector contains information sufficient for us to both audit the sector and to reconstruct data from the sector. How it happens. In version 2 consensus, we have proof of space used as part of the encoding. So what we're doing first is we take those original chunks from the record and we apply ratio coding. The way ratio coding works using polynomial mechanism that we have right now, basically every odd index is the source data. Every every even index will be the parity. So we have source parity. We have source parity. That's why these are ratio coded. So these are piece 0 chunk 0, piece 0 encoded chunk 0, then piece 0 chunk 1, piece 0 encoded chunk 1. So that's how we have it essentially in memory. Yeah, go ahead. We cannot hear you. You're muted.
Sorry. So the piece is that 31 byte thing, right? Or you leave out the last 2 bits. Is that a piece? Or
no, the piece is this whole row. It's record plus commitment plus witness. The record contains multiple of chunks, and every chunk is 32 bytes.
Okay, so every record, I see.
It has up to 254 bits of information in it, but it is 32 bytes.
Okay, so the chunk is a 254-bit thing, is it? Okay.
Yeah. So like at this point, it is guaranteed that if this is a valid piece of the history, these chunks are guaranteed to be possible to create a scalar from. Okay. So the first step is we are creating erasure coding. We have twice as many of these. In parallel, we kind of can derive proof of space. For that, we have a seed for a particular sector, and for a particular piece offset, like we have 4 offsets, 0 to 3. And we generate, for every index that we have erasure coded here, we generate equality, which is basically like almost proof. Like there is a proof, but there is part of the proof which is quality. And for encoding, we just need quality, which is faster. So we just generate a bunch of those qualities, and it is a probabilistic process. So about 2/3 of the time we will have a quality in proof, and 1/3 of the time we will not have quality in proof. So when we do have, which is denoted by plus here, we will take that, which is 32 bytes, and we will encode it or like XOR it with this, which is also 32 bytes, and we will get P0 chunk 0 XOR P0 quality 0. In case we don't have any proof here, we will just copy the original one as is. That's how we end up with this situation, where we are just encoding chunks which we can encode. And we basically do this operation 4 times in this case. We do the same for the second piece, the third piece, and the fourth piece. And we basically have like this kind of construction. It's not exactly the same in the implementation, but like the mental model, what happens, right? But the goal for us is to actually create a sector which contains as many chunks as we had originally, but we want them to be encoded. So why we are doing erasure coding here? One of the reasons is because here we only have 2/3 of the qualities. By having twice as many of these, there is a pretty good chance that half of them will be actually encoded properly, and we want them to be encoded because unencoded cannot participate in farming. They're not eligible for generating solution. So what we do then, after we did encoding, we will pick the first 2 chunks which we were able to encode. So in this case, this one and this one, for them we had proofs and qualities. And then we will also create a bit field which helps us later, where we will be putting 1 in the case where we did pick encoded chunk. If it's not encoded or we didn't pick it, it's 0. Okay. And we again do it a few times. There is a separate case here where we have only 1 encoded chunk, in which case we go back to start and we pick unencoded chunks as many as we need to fill half of them, right? So in this case, we have 0, 1, 0, 0, but only 1 of them is encoded actually. In this case, we have 3 encoded, so we pick the first 2 and the rest of them are again ignored. Okay. So we did it 4 times, and then we construct our sector. The beginning of the sector is what I called sector contents map, which basically is all of those bit fields concatenated. And once we have those bit fields, it is basically sufficient for us to decode the data back. How we can do it? Let's say we have this one. So we know that we will write exactly 2 chunks. That's our target size. And we know that the only one of them will be encoded. And it was at the second test bucket. This is index 2 vertically. So we know that this one is encoded, but we need 2. So we must have picked the first one as well. So we know the contents of our part of the basically we know that we picked these 2 chunks out of all of them for the second index, and we know how to reconstruct it later. So this is like the most compact representation of the contents we could have, just 1 bit per chunk. That follows by the chunks that we pick. So we basically go through all of these columns vertically. I have reconstructed them here. So these are the chunks we pick for this S bucket 0, which is basically the first one here. Here we don't have anything in index 0, then here, and then here. And I did it for all 4 S buckets from 0 to 3. And I just write all of them for S bucket 0, all of them for S bucket 1, S bucket 2, and 3. And then at the very end, we know how many pieces we have. We can store commitments and witnesses for those pieces because that will be required when we want to actually generate a proof. So the input is we have offsets for which we deterministically figure out which pieces we want to get from the history. And then this is what we write to disk. Does it make sense? Any questions?
I have a couple of questions. Could you repeat once more? Probably I missed that. How these chunks goes separated to the S buckets? How they're related in this middle of the picture?
Yeah, basically, as buckets are like vertical columns. So in this case, we have 4 as buckets because after erasure coding, we have 4 columns. And only some of them will be filled by a particular record. But in general, like almost all of them will be filled at least to a degree. In practice, we have 2 to the power of 16 of these columns, which is like 65,000 and a half. But for demo purposes, it's much less.
Okay.
Any other questions?
And could you describe once more how we calculate qualities for that?
It's just Chia proof of space. You basically generate tables for Chia. You give it a seed, then it will generate tables, and you can probe it at index. So we probe it at index 0, 1, 2, 3, and so on, how many S buckets we have. And for every one of them, we will either have a proof and quality, or we will not, like no proof.
Like we were initially using proofs, but the difference is in Chia proof is like 64 values and equality is just 2 values that are part of those 64, which is much faster to get. So for encoding, we're using qualities, and equality, if it exists, it indicates that there is also proof, which is exactly what we want to know. So it's just like 2 values out of the table. It's not really like equality in like a qualitative sense.
Yeah, and you can extract quality from the proof. So when we actually generate proof of archival storage, we will include proof. And during verification, you can extract quality from it. You can do the encoding. You can verify that everything matches and so on.
Basically, a partial proof. Yeah.
Okay, so you should have like high-level idea what we want to achieve, not necessarily how we actually do it. So what I described to you is basically a section about plotting. And I will, let's see. We have quite a few commits. I think I will skip those that are like preparation. And I will just go into the implementation itself. We can later go into the others if there are any big questions. So as I mentioned, there are many changes, and it's generally recommended to just look at new implementation as completely new implementation rather than as a diff. So let's do that. Let's open plotting in a separate tab and just go through it. So if we go into the specification, the first step is to basically get those pieces from the history, separate witness and commitment from them, and store them somewhere alongside the plot. Then we will take our records, slice them into chunks, and then for every chunk, we need to do the encoding. So let's see what happens here. We have a function plot sector. We verify that some of the input parameters are actually make sense, and then we derive sector ID, and then we have kind of the amount of history we have in the blockchain, which is current sector index. And this is a future thing that will be used for expiring sectors. So we have some expiration on the protocol level, and we will basically consider that sector invalid at some point, but it is not enforced right now. And then we basically have a vector of indices. These are the indices here that we are downloading from the history of the blockchain. So we basically go through offsets from 0 to how many pieces we have. According to specification, is 1300. In this pull request, it's just 32. And then for every one of them, we, from the offset, derive the piece index. So we know which piece we need to download. And then it's very simple. We just go and retry and try to download all of those pieces we've just collected into this thing, which is called raw sector. So just pulling them from the history. If I go to, let's see, to the sector, I think raw sector is defined here. Oh, wow. What is this? This is not very readable. Okay. Raw sector is basically the same pieces that we download, but we slice them into separate vector of records and then vector of commitments plus witnesses separately. It's like instead of vector of pieces, because we need to work with them that way. So we have those, and we can start to do the actual encoding. What we'll do, we will go again through piece offsets, starting with the 0 to how many we have. We will zip it with the records themselves. And then we also will create a sector contents map. Sector contents map is a somewhat sophisticated data structure. It has, let me open this as well separately. Sector contents map. Yeah, so it has two fields. Only one of them is actually stored on disk. This is the bit field. We have a certain number of records. For each of them, we will have a corresponding number of bits for S buckets. These are these bits that we have. So we have a vector of them. Size of the vector is the same as number of pieces we have. And then there is a denormalized piece of data structure, which basically says how many encoded chunks we have in every record. That helps because we are doing that computation, or like we would have to do that computation heavily in many places. So we would have to go through the bit field, which is 2 to the power of 16 bits, which is quite a bit. And we need to count ones or count zeros. It's just expensive when you do it a lot. So we denormalize that and store it alongside, but it's kind of technically redundant. And then this contents map has a few methods that allow us to kind of work with the history of the sector. We can know how many encoded chunks we have. That's the data structure we store. And we can also iterate over record bit fields if we want. We can also get sizes of each S bucket, because as you see in the diagram, they are not necessarily the same size. So there is a way to, basically there is a way to interpret those bit fields in various different ways. There is also a way to get to map record chunks to plot. So if you want record chunks for piece offset 0, it will give you information how you can find it in the actual sector, like where it's placed. Because again, every bucket is different size, so offsets are not necessarily known deterministically. And there are some other methods. So basically what we'll go, what we'll do, we will go through bit fields for every record, and we will derive first the proof of space table. And then for every record that we are dealing with, we will iterate over chunks and erasure code it. And then we will try to derive quality for it, for every chunk. And if you don't find it, that's fine. If you did, we will set corresponding bit to true or 1, and then we will XOR it together. That's the operation that we have over here. If you don't, then in this particular case, we will just skip it, and we will count how many encoded chunks we were able to produce. And then however many of those chunks are not sufficient, we will just grab the remaining number of chunks from unencoded. There are many iterators here, but that's the gist of it. If you want to like look more closely, you can see that there are some optimizations here, and all of this stuff is done in parallel. But basically, at this point, what we are getting is we are getting two results. We get this stuff, which for efficiency purposes, we are storing in the original record. And we are getting the bit fields. And those bit fields are stored in our sector contents map. Then once we have all of that done, we can basically write plot to disk. So we create a buff writer for the output, which in our case will be a slice of the file corresponding to sector. And there are some functions that allow you to estimate the size of the sector given number of pieces. So in here, we have sector size function. You just give it number of pieces in the sector, and it will give you the exact byte size of the result. And here again, we are going through S buckets one by one. We reach out to the sector contents map, and we will ask it to give which piece offsets we want to actually get. And it will tell us whether the chunk is encoded or not. And we will, what we're doing here. Yeah, basically we are computing offsets where we need to write it, and we extract that offset from the record. This is the piece offset, and this is the chunk basically offset within that record. And at the end, we have, before that, we actually wrote the sector contents map. So we wrote this small part. Then in the cycle, we are, in here, we are writing chunk by chunk all of these guys. And then towards the end, once we wrote all of that, we just write metadata one by one from the sector metadata. And basically, that's the whole plotting. There is an old function for getting for downloading pieces from the DSN. It has changed slightly, but the logic is the same. And that's basically the whole plotting. So plotting is quite straightforward. Once you understand what is happening, there are some tricks with iterators and make it parallel and make it somewhat efficient. Hopefully that makes sense. Any questions about how this works? Shamil looks concerned.
I think I need to read proof of space page. Because this kind of how do we generate these qualities, and as buckets, it doesn't it didn't reflect it on the page on the spec. So
yeah, you treat it as a black box. You really treat it as a black box. You just for every record you just create a proof of space table, and then for every chunk you just call find quality. It will give you option of quality. If you don't have it, you don't have it. If you have, you will do encoding.
So one question is like, so in a bucket, right, which is basically a column, right?
Mm-hmm.
You have holes because
yes.
the corresponding chia table did not have an entry, right?
Yes.
So what are the chances of having a hole in a? So what I mean is like,
chances are pretty high. So if you look at the this diagram intuitively, you have twice as many S buckets as you have chunks in every record. So every S bucket will be on average have as many chunks as number of pieces divided by 2. In practice, there is a more complicated distribution, especially because not all of the chunks are present, and if they are not present, we will take unencoded chunks from the beginning. So there's actually like a skew towards the beginning of S buckets in terms of how full they are.
So basically, I'm visualizing that as a matrix where some things in the column are not present. Is that correct?
Exactly. So like in this column, we have basically a hole at index 1 because the red one is not present. In this case, we have a hole at index 0. In this case, we have 3 holes and 3 holes here.
We're not
but in total, we have...
I'm just saying we're not really writing like zeros instead of things that are...
Yeah, we just skip it completely. We have information required to understand where holes are after the fact. We didn't really find any way to store it more compactly than this.
And how is this sharded? Like every farmer is responsible for a column? Is that...
no, every farmer will store the whole sector. So this is a sector unique to a farmer. And every plot will have multiple sectors. This is just one of them. So you basically repeat that process as many times as you need to fill your disk. So everything starts in the plotting and other places, everything starts with the sector ID. And sector ID is derived from your public key and index. So if you have like 10 sectors, it will be 0, 1, 2, 3, 9.
I'm looking at figure 4 in the doc you sent yesterday. Piece to record.
Yeah. So on the left, you have global history. And on the right, you have records which, or like pieces that are assigned to a particular sector. And how you assign it, you create a sector ID, and then you derive piece index for that offset, for every offset in the sector.
Yeah. So basically, a farmer is responsible for a record assigned to him. Or rather, archival segment is broken into pieces, and each piece is assigned to some farmers, basically. Right?
Yes. So here we call it raw sector, and we have records, but you also need to store commitments and witnesses just to be able to prove it later, or we add it towards the end of the plot, or like sector.
So the farmer basically stores at every stage he adds a row to his storage, if I understand correctly, right?
Can you repeat that?
So at every stage, whenever a new archival segment is added to the plotting system, the farmer gets one or more rows in the.
No, for the farmer, nothing changes except when the sector expires. When the sector expires, they will throw it away. They will do the same calculation again, and because the history has changed, with some probability, they will be able to use one of those newer pieces towards the end.
Basically, when the farmer joins the network and they say they pledge like, I don't know, 10 gigabytes, so they can plot like 10 sectors according to the spec, well, a little less. And you do plotting like all at once. And so if you have a sector 0, you do a selection of 1,000 pieces. Well, right now it's implemented 32 pieces, but in the spec it's going to be around 1,000. You encode them as the way Nazar designed, described. You save it to disk. You do that for all as much space as you can pledge, and you basically seal it, and you can participate in farming. Now, at some point, some of those sectors may expire, and then you just redo this process. You download new pieces that were assigned to you, you encode them in the same way as before, but you're not doing it continuously.
Okay, so can we move on? There is another component that is part of this first commit of the implementation. Initially, it wasn't here, but after hundreds of rebasings, it did end up being present. It's reading module, and the observation is that we need reading of a particular record both for proving phase and for DSN extraction of data, useful data from the network. So that's why we have this thing. There is, again, one function, which is, no, there are many functions here. I think the most high level is at the bottom. It's called read piece, and you will give it the offset. You are supposed to know which of those offsets your piece index corresponds to. That's something we store in the farmer in the memory. And then you will also give it the sector ID, metadata for sector. This is like a reference to the sector read into memory or memory mapped sector, whichever you have, and then a ratio coding instance so you can decode things. And then you basically do kind of the reverse process. You read the sector contents map from that plot, then you read chunks from that plot, then you read commitments and witnesses for that record from the plot, and then you assemble a piece together. How you do that? For records, you need to read chunks first, and that's this function. Basically, you will get this stuff. You will get as many elements as you have as buckets, but there will be some holes. However, chunks will already be decoded. So you will kind of get P0, C0, and then you will get P0, E1. That's what you'll get for the very first offset. How we do that? We basically allocate memory, and then we iterate. Oh, yeah, Shamil, go ahead.
I have a question. When we read chunks, do we do random access or sequential? I think random access is correct answer. Is it?
Yes, it's random access, and it's done in parallel.
So even for chunks from the neighboring chunks within the piece, we do the random access because we do it from
they are stored randomly.
Because from random as buckets, yes. Okay, thank you.
Yeah, like if you look here, like one blue here, one blue over there. Like they are not contiguous. So here we just iterate over chunks. For every chunk, we need to know where it is in the plot. And then we also need to know sizes of these as buckets. Like we need to know how many entries we have here so we can jump into the correct location. So this part is where we store the result. This is the information where within S bucket we have our chunk, and this is essentially where S bucket starts in the global sector. And then again, it's quite simple. If we have information about a particular S bucket, because remember, we have holes. If we have, then we will calculate the location of the chunk, and then we will go into the sector like into memory slice, and we will basically slice out that chunk from there. And if it was encoded, we will decode it in place, and then we will return information. No, we will return the scalar as an option from here. So basically, we will get a fixed size array of those chunks, half of which will be empty. And then once we have those, at the very end, we can do erasure decoding, and we can assemble the source from them, which is quite simple. Reading as commitments and witnesses is kind of clear how it's done. And there is a function for reconstructing sector contents map, which is, again, kind of obvious how to do it. Reading of chunks is a little bit tricky. That makes sense? Okay, so this is the first step. We have a plot. We know how to read from the plot. Now we need to do the auditing and proving. Thankfully, auditing is very simple. And unfortunately, proving is not simple at all, and it's actually quite compute intensive, at least at this point. So let's look at the auditing first. We had several changes here. Before we had just one module called farming. There was another module plotting. Now we have proving, reading, auditing, and plotting all separate. So we will look at the auditing first, which is part of the farming process. And auditing is really simple. Like there is 100 lines of code here. Basically, for every sector, for every public key plus index, we derive sector ID. We will derive which we will derive a challenge, and then we will derive which S bucket, one of those columns, is actually eligible for binning. And it should be one of them. And we will basically read that whole column. So we will read like 3 values here or 1 value here. And then for all of the chunks in there, which are actually encoded, we will be able to try to produce a solution if that chunk happens to be within solution range. So that's basically how we offset. We seek to a particular location, we read it, and then we slice it into chunks. And then for every chunk, we have actually a notion of audit chunk. So remember, these chunks are 32 bytes, but solution range is 8 bytes, and audit chunks are also 8 bytes. So we take every 32-byte chunks, we chunk it into 4 8-byte audit chunks. And then for every one of those, we will basically do the check whether that offset within chunk is actually in solution range. And if so, we will return that as chunk candidates. So these are basically chunks within which are audit chunks, which are potentially eligible for solution, but we are not quite sure yet. Because they might not be encoded, we don't yet know at this point whether they're encoded or not. So in most cases, they will not be, and that will be the end of your audit. All you need to do is to read one S bucket. We already have cached the location of that, so we basically read like 32 kilobytes at most, and we are basically done. If we have some solution candidates here, then we actually need to try and do the proving. So I just want to make sure that this phase is kind of clear. We have S bucket, we have some chunks. Every chunk has audit chunks in it. For every audit chunk, we do the check whether it's in solution range. If so, we return. and we will try to produce a proof later. Like if you go to this packet, it looks quite similar to that. Audit, we derive index of S bucket, and then for every audit chunk, which has the same size as solution, we basically XOR it with the challenge. We check if it's within solution range. That's it. The proving is more complicated stuff. Okay, let's go into the proving phase then. Proving has changed dramatically. I don't think there is a point in reading the farming that was before. The way it's designed is these solution candidates are a data structure, and for some testing and benchmarking and other purposes, it is helpful for that to be clonable, which is why there is a clone derived on this thing. And you can clone it, and let's say before every iteration of benchmark, you can just cheaply clone it. And then when you actually do the proof, you will turn that into the iterator. And that iterator will give you solutions. Okay? So the iterator is this data structure. It has a bunch of fields like reward address and other things that you need to actually produce the proof. And for every, remember, for every S bucket, we have multiple chunks, and each chunk has a few audit chunks, a few of which can actually be winning. So what we are doing here first, we are constructing a chunk cache, which is basically some information that every audit chunk within that chunk will be requiring. And that includes, let me open the data structure. Yeah, it will be the chunk itself as a scalar. It will be offset within S bucket. And then there will be record commitment for corresponding record, record witness, and then there will be chunk witness that this chunk is part of the record, and that is proof that record is part of the history and proof of space for that record. So basically, if you don't have the chunk cache yet, we have not yet processed a single audit chunk for the chunk. We will do, again, proof of space table derivation. Then we will read record chunks from the plot. This is one of the functions from reading module. Then we will extract the chunk that we actually care about in S bucket. So we have all of the S buckets for the record, and we basically index into the S bucket that we're actually proving right now. It must be there because otherwise we wouldn't get a candidate in the first place. Then we need to recover all of the chunks. We need to create a polynomial out of that. And then we need also record commitment and witness. And then we can find proof of space for, again, the same as bucket. This is a proof, not just quality. And then we can generate basically a witness that the chunk, let's say this one, before it was actually encoded with the proof of space, it was actually part of this thing. And due to some KZG magic moon math, we can prove that that actually corresponds to this commitment because we committed to all of the chunks. But because they are erasure coded in a special way, even if you pick erasure coded one from here, it still proves against this commitment. So basically, we will attach a proof that this is part of this commitment, and we will attach a proof that this commitment is part of the global history of the blockchain. That way, we prove it all the way from an individual chunk to the global history, and we will include that chunk in the solution. So proof of space basically proves that we have correctly encoded this thing, and then we collect all of those things, chunk witness, record witness, commitment, chunk itself, its offset, and proof of space into this cache. And then for every chunk or the chunk that we have, we will basically compose the solution data structure. I will go through the verification phase later that will clear up how we actually use all of these components. But these are sufficient to verify everything we were doing, except one thing that I will show later that we added a little bit after the fact. The rest of this file is like error handling and transforming that data structure into the iterator. At the bottom, we have iterator construction, where we need to read the sector from disk, and then we need to reconstruct sector contents map. We need to calculate some stuff about these buckets, just like technical stuff, so we can iterate over things. The important thing that we are not reading any of that. We don't do any of that unless we have chunk candidates. So audit is super fast, like it's milliseconds. Proving is currently seconds, which is not nice, but hopefully we'll fix it. Any questions about this one?
Could you remind us what this audit is? What is the process about?
Yeah, so we have a sector. We have a challenge from consensus that there is a new time slot, here's randomness, try to solve it. And our goal is to go through every sector, figure out which S bucket is potentially eligible for winning, and then go through all audit chunks in that sector, or in that S bucket, and see if we actually have something that's within solution range. If so, then hooray, we can actually produce a solution.
So it's a part of the proving process, basically.
Yes, we first see like what is winning, and then we need to prove to the consensus that we do actually win, and that's the proving part.
Okay.
I mean, if you,
Very
you do
quickly
audit
figure out
always,
if we win.
Yeah, you do audit always, but proving you do only if you have a winning chunk.
So this is why we separate those processes.
Yes, we have a very quick way to know if we win, but it's quite hard to actually prove that you win.
Okay, thank you. I got it now.
Okay, any other questions so far? All right. There are many changes in every of these commits across the code base, because if you change the solution data structure, it is used in many places. So I have updated all of those places at the same time. So it still compiles. It doesn't actually like pass the consensus checks, but it does compile. There is only, like in this commit, there is only one test file from SQLite client which doesn't compile. The rest of them compile just fine. Okay, the next step is to do the verification. Yeah, quite naturally. And all of that verification happens in the separate crate that is called Subspace verification, I believe. Yep, in here. And let's see. What you would usually call as a user is verify solution. There are several steps to it, but in general, you will do the verify solution. You will call it from two places logically. One is when you verify the block, because block will have a signature on top, but within it, it will have a solution that allows farmer to produce a block. And the other one is a vote. We have votes in our system, and there are signed votes, which are basically like block. It has solution, and it has a signature. Signature you need to verify separately, because how you extract a signature where it's located is different for block and for the vote, but the solution within it is the same. So you would verify solution here, and you will verify signature elsewhere. So here, first we need to provide some parameters for the verification process. We need to know what the randomness is right now. We need to know what the solution range is right now. And there are also additional checks to verify whether the header contains correct global randomness based on the previous block, which is not reflected here. And there are also potential parameters for the piece verification if we can do that, because we cannot do that in the verification phase in the substrate, where we just received the block, but we didn't import parent block yet. We can do some checks, but not all of them. We don't know what the global history is at that point yet. But generally, the mechanism is similar to all of the other files we've seen. We need to derive sector ID first. Then we need to derive global challenge from global randomness. We take global randomness and slot. Then we need to identify sector challenge for a particular sector and global randomness. And then we need to figure out which bucket we're dealing with. So at this point, we already have sufficient information to verify proof of space. We know the S bucket, which is the index we use for quality checks. And we also have proof of space in our solution. And we also can derive the seed that we used for our offset and history size that farmer, like the point in time at which farmer create this plot. So we can verify that the proof actually corresponds to this table we generated. We have all of the components to actually verify that. If we verify that, as a result, we get quality. Quality allows us to do decoding or like re-encoding of the chunk. If this proof of space doesn't match, something went wrong, and this is invalid proof of space, goodbye. If everything is okay, then we can basically go to this step. We can do the XORing. We have included original chunk in the solution, and we will basically turn that chunk using XORing, and these are SIMD instructions for XORing, so it's a little bit faster, potentially. We basically get encoded this A XOR B kind of thing. And then we need to be able to get audit chunk from that chunk. So this is encoded chunk, and we get audit chunk that was actually used to produce this solution. And once we have that audit chunk, we can check whether it's in the solution range. For that, we extract the distance, and then we check that instant distance is not more than half of solution range, because it goes both ways. Once we know that the chunk or the chunk is correct, then we can verify that that chunk that we've just encoded here, like this original chunk, is actually part of the global history of the blockchain. So for that, we will check the record commitment, which is commitment to all of the chunks in the particular record. And then we will take chunk and we will take witness. And we will basically use KZG verification to make sure that the offset at S bucket that we are trying to prove actually matches to this chunk. So this is the chunk at this S bucket offset after ratio coding of this record, and everything's okay. This is the local check, the last check we can actually do without having access to global history. We are just ensuring that everything within the solution is self-consistent. What we cannot check yet if whether this is part of the global history. So for that, we need to have this like additional parameter, which is segment commitment for a particular piece index, basically. So we have a sector ID, we have an offset. In solution, we will derive piece index, and that from that piece index, we will try to prove that our solution contains a record which is part of that history. And that is a separate function, check piece. It is quite small in here. Yeah. Basically, we check that if we hash record commitment, that it actually verifies using KZG. And at that point, we basically know that our solution is correct. So as long as the public key included in solution is the same public key as used to sign the vote or the block, we can produce a block. Everyone looks super confused.
Actually, it became better after your explanation. I definitely will reread spec and also proof of space and several times your PR, but it's
yeah. If you like read the function top to bottom and you read the spec top to bottom, it should more or less match. So it basically says that we have a winning chunk audit chunk. It is a chunk offset within corresponding S bucket, which is chunk of the record. We will get it. We will determine if it's, oh, that's a different point. Yeah. For the verification, we will rederive sector ID. That's what happens first. Then we will rederive challenge for that sector. We will identify as bucket. We will do a violation seed. And then we will check proof of space. We will get quality out of it. We will verify the chunk is actually part of the history. And then we will ensure that the record belongs to the history of the blockchain, and signature is kind of outside of the brackets because it depends on whether it's a vote or a block. Yeah, go ahead.
Can you help me understand the S buckets? Like, is there an intuitive way to understand this term? Like, what, like how is why is named as S bucket? I still don't have enough like idea
S
how.
bucket is an index of a ratio coded record. So you have original record, in this case, 2 chunks, then you get 4. This is 4 S buckets.
So
and in the whole sector, it will be a column throughout every piece. So it would be every S bucket 0 would be the 0th chunks of every piece. If they had a proof, there might be some holes and so on until the very end.
So like here vertically, I moved like XOR into the middle, and it will like filter out those that were encoded or included otherwise. And then like if you draw a line vertically like this, here we have a hole, and this, and here we have this. These are like the 3 that we have in this bucket.
Why do we need to fill those holes with non-sort data when we have bitmap?
We need to have exactly half of chunks for every record, otherwise we cannot recover the record. So whether encoded or not, we need to have something so we have sufficient redundancy.
It's just in like almost around 1% of the cases, our like proof of space table does not really have enough proofs for us to encode everything. And so in that small percentage,
it's even better. 1% of records have at least one chunk that is not encoded. But 99% of records have all of the chunks encoded. So this is like a special case when we are using unencoded, because otherwise we will just lose data.
So you are saying that 1% of the user's data basically useless for him?
No, 1% of the records will have some data which is useless.
No, I mean that they won't get rewards for that because there were no proofs. And
yes,
just
1% of the records they plot will have some of the chunks which are not eligible for rewards. But it's like,
but not the whole
I don't know, a few percent of 1%.
So less than 1%. Okay, thank you.
It's like a fraction of 1%, maybe like, I don't know, maybe 0.2% or something like that. If you don't do the erasure coding, then about 2/3 of all chunks will be non-eligible, which is a problem. Which is a big problem. You can just not store them, or you can store them once and not for every sector.
Okay, I just feel this name S bucket is not super straightforward to connect with the encoded records.
Yeah.
Yeah, I think it should be called column or something. I mean, that's how I'm visualizing.
That's why I visualized it that way. Like this way, it makes sense for me. But it was described in a way that wasn't super intuitive for me before I started implementing in this spec. So maybe there is like a third way to visually represent it that will make more sense to you. This
basically,
is like how I have it in my head.
Consider it like Jeremiah invented the name the bucket because you can like visually imagine it as like you're taking this chunk, you're taking the quality from a record. If there is a quality, you put it in a bucket, then you take the next one. Oh, if it's not encoded, you throw it away. Then you take the next one. Oh, it's encoded, you put it in the next bucket. So that's sort of what he envisioned with this.
There are K buckets in Kademlia. I believe there are S buckets in other protocols. Just like a term used.
Actually, I always get confused with this piece and record also. Maybe they should be called something else. In the sense, piece is basically the user data, right? Record is basically user data plus commitment plus other stuff, metadata.
No, record is the data. Piece is record plus commitment plus witness.
Okay. So even now I'm confused. Okay. So
if you are confused, just go into the source code. Let me show it to you quickly. let's see, creates subspace core primitives, pieces, and piece, let's say, yeah, basically if you go to a piece and you will try to see, okay, it's derived, yeah, the references to this, you will have this method, which is split. So you can split every piece, or like its contents anyway, into record, record commitment, and record witness. At least this way you can like quickly verify what it is composed of.
Yeah, I mean, you can read the code and figure it out, but when you just look at the specs and stuff, right? It's always confusing.
I agree. Like I work with pieces for like 2 years now, or maybe more. So it is kind of like burned into my brain at this point. I can imagine this is not super intuitive at first.
Maybe it should be called consensus data or consensus blob or something like that, right? Because that's what it is.
Blob would be record. Yeah, it's called blob in Ethereum. There is also like a glossary that we try to maintain up to date.
Yep.
That Nazar initially reached, and then I updated for the new consensus. Yeah, you could search for like naming, and then it has like names for things what we refer to.
Yeah. So after I implemented all of this, I noticed one thing. Nowhere in the protocol we actually verify how many pieces we can have. Why it's important is because you need to audit every sector. So the less sectors you have, less reads you need to do, at least for the audit, right? Because you will need read at most one column or like one S bucket for a particular sector. So I didn't want to rebase everything like 10 more times. So I've added that at the very top. We had a constant which was called pieces in sector, which was like a global constant. It was replaced with the consensus parameter. So in the runtime, what to show you? I think SP consensus subspace. We have a runtime method, which is max pieces in sector, which basically defines upper bound. So this is how big your sector can be. It can be smaller. Doesn't make a lot of sense because you will spend more time, more resources auditing, but it will also use less memory. So maybe in some cases it is beneficial. The gist of it is that we have this max pieces in sector parameter, which is an upper bound. We also have, and I suggested this to Shamil already, in the farmer, we have a CLI parameter where we can actually limit for our sector how many pieces we want to have for like testing purposes. You can define your sector is one piece, and everything is much simpler. And then in verification, we will have another parameter. Oops. And we will check that when we get this offset is less than our max pieces in sector. Because if it's more, it's a problem. You have sectors which are more than we allow. And the idea is that in the future, we will probably increase this number. We will allow bigger sectors as people pledge more and more space. But initially, it will be some kind of value. And specifically, that value is in the specification 1300. This is at most how many pieces you can have in a sector. It's like a small addition on top of all of those parameters. Plotting, verification, proving don't change. We just need to change the verification. And for testing purposes, if you look at something like SP Light Client in the tests, you will see that where it is in the mock, this number is actually set lower. So for testing purposes, we have smaller sectors. For production purposes, we'll have bigger sectors, such that our tests are running a little bit faster. Another thing that you may have seen from the previous commit and something I mentioned in the description of the pull request, let's go to the verification again. There are many generics with the proof of space implementation. In the verification specifically, oh, we have it opened, I think, here. We have proof of space table generic that we use to generate our or verify proof of space. The reason for that is that proof of space derivation is by design kind of expensive, and we would like to run tests faster again. So in the proof of space implementation, there are actually two implementations. One is Chia. It uses the Chia proof of space library. And there is another one, which is just a shim, which does some really naive stuff, but it works like in picoseconds. So for testing purposes, we have smaller sectors, and we don't actually use real proof of space, but we have this shim which behaves kind of like real proof of space, even though it's not secure. And also, if you go, let's say, in verification, we also fixed tests. So if you go to something like SP Light Client, which is Light Client implementation for Subspace, and we go to mock, I think. No, it's in tests. Let me open it. Camera right in front of the screen. We are actually reusing plot sector. We're actually reusing our Subspace Farmer components. So we are using the same functions as we use in production for plotting. We just use fake proof of space at the top. It is defined as shim, I believe, somewhere. And then when we are doing verification, we also verify solution with the regular verification function. So previously we were like manually kind of plotting things. Now we don't need to do that. We can just reuse generic functions. I think that's the most of it. There are some preparation commits before this, and there are some kind of optimizations, and the very last commit actually decreases parameters. So number of solutions that farmer will try to produce per sector is just one. Otherwise, it's just too much time. And we have 32 pieces in sector max. So you can actually prove within time slot. And the time slot itself is 3 seconds instead of 1. So this last commit will hopefully roll back once we fix performance. A little bit over time, an hour and 5 minutes. Hopefully when you read it again and you look at the spec, you will see a little bit more familiar stuff than before. Any other final questions? Okay, thanks everyone for asking questions. And yep, we'll be stopping recording, and maybe we'll have one of these at some point again.